Hello everyone, and welcome to this recording of my first tutorial on a deep dive into the world of ion mobility spectrometry. I'm sorry you weren't able to join us the first time. I realized it could be a hard time for some people, and I completely forgot to hit record, so you get a special recording. Unfortunately, you missed our fun Kahoots quiz though, where we quizzed on some of the ion mobility facts and concepts. So hopefully you can join us for our tutorial part 2 and then join in on the fun for these quizzes. So let's get going. So today I'm going to talk about what is ion mobility spectrometry and what are the differences between the diverse ion mobility methods. So the drift tube ion mobility spectrometry, traveling wave, field asymmetric, differential mobility analyzers, and trapped ion mobility spectrometry. There are many other ion mobility spectrometry types actually, but I'm just going to cover these 5 today, as a lot of the others aren't used quite as often as these. I wasn't able to get to the benefits of using ion mobility or the challenges related to data analysis last time, so we'll cover that in part 2 of the tutorial. So this slide I think is a fun slide though, because everybody probably has run into an ion mobility spectrometer at some time, especially if you've ever flown. So if they've ever swabbed your bag or used the swab on you, they actually put that swab into an ion mobility spectrometer, and usually one from Smith Detection or some of the other manufacturers, but it will look for specific explosives that could be on you or in your bag. And that's sometimes there's false positives though, so if you've ever been pulled aside and had to be checked further, that's because the ion mobility had a false positive with the reading from you. It's also commonly used in the military, and you can see some of these handheld devices, and they actually have backpack versions or other handheld devices where the people in the military can carry them around and get these explosive readings so they know if they're in a dangerous area. It's also being used with different breath analyses too, so this is kind of another exciting area for ion mobility. So today we're going to talk about how ion mobility, all the different types, define how an ion drifts through a gas under the influence of an electric field. And this is defined based on the separation of using mass, charge, size, and shape. However, what distinguishes the different ion mobility methods are the electric field, the pressure, the gas composition, gas flow, and temperature. And we're going to talk about that today so you understand why the different methods can be distinct. So ion mobility by many people has actually been thought to just be a more recent technique, especially since the Synapt was commercialized in 2006. A lot of people thought that was more of the beginning of the ion mobility spectrometer. But it actually goes clear back to this 1896, and I'm going to highlight a few important dates for you guys. So in 1896, Thomas and Rutherford constructed an apparatus to study the mobility of ions in various gases. So this was some of the first ion mobility research done. Then in 1961, McDaniel coupled ion mobility to a magnetic sector instrument. In 1970, the first commercial ion mobility spectrometer was introduced from plasma chromatograph, and it was about this time, 1968-ish, 1969, when the military started using ion mobility in their explosive measurements. Then clear down here in 2006 is when the Synapt started and commercial traveling wave was available. So another interesting part on this slide is if you look at the publications per date or year, we can see that the publications are rapidly growing through time, and especially in this commercialization period, we can really see them grow. Before this, ion mobility was mainly available to people that built their own systems. So it wasn't massively available to the scientific community. Now, if you want to, but pretty much every vendor has a different version of an ion mobility spectrometer that you can put in your lab. So what are the differences between the diverse ion mobility techniques? And so we're going to start talking about what makes drift tube ion mobility different from trapped ion mobility and some other information. So when someone says I perform ion mobility measurements, it's similar to saying I drive a car. So do you drive a smart car? Do you drive a sports car? Or do you drive a bigger car that's a pretty fancy car that you can maybe put some of your family in, but not necessarily a family car for most people? So questions you want to ask that person who says that they're performing the ion mobility measurements are, what type of ion mobility are you doing? Which buffer gas do you use? Which instrument do you use? What is your resolving power? What's the pressure of your system? And how rapid are your measurements? And all of these will help you learn more about how they're conducting their experiments. So ways to separate the different techniques are, one way is by electric field. So whether the instrument has a static electric field or an oscillating electric field. And some of the techniques with static fields are drift tube ion mobility, the differential mobility analyzer, and trapped ion mobility, where oscillating electric fields occur in field asymmetric IMS and traveling wave IMS. And so if we go to some nice schematics, we can see how these are applied differently. So here in our drift tube ion mobility, we can see that the voltage drops per distance. So it's actually uniform throughout the system, but you'll apply a higher voltage at the beginning and a lower voltage at the end. And so you could say something, a lot of times a common electric field that would be used in drift tube ion mobility would be something like 12 volts per centimeter. DMA is also the same, where trapped ion mobility, you start to ramp that electric field, and that helps get different ions out of your system. In field asymmetric ion mobility, we see that our electric field goes up and down based on how the molecules are traveling through the system. And in traveling wave ion mobility, we can see that this wave is basically pushed throughout the system in kind of a surfing type of way. So that wave is moving, but that means your electric field is going to be different as your molecule goes through. So then we can also classify them based on temporal separation or spatial separation. So whether your molecules are separating as they go through distance or in space. And so here our drift tube, traveling wave, and trapped ion mobility are all temporal separations. You can also see that I put trapped ion mobility also in spatial separation, because you can make the molecules, you can adjust the way that the instrument's working and get both a temporal separation and a spatial separation. We can also do field asymmetric and differential mobility analyzers and put those into the spatial separations. So here, drift tube, TWIMS, and TIMS, you can see the molecules all separate as they go in distance. Where here with FAMES, DMA, and TIMS, again, TIMS, based on how we're ramping that voltage, we can get specific molecules out for different time frames. FAMES and DMA have specific slits where other molecules can be pushed into electrodes and killed, and basically the molecule of interest can go through that slit. So I'm going to start to give a little bit more detail into each of the methods, and I'm going to start with drift tube ion mobility because that's the one I've been doing for the last 20 years, and so I usually always start there. And so drift tube ion mobility uses a drift tube, so big surprise on the name, and you put a buffer gas into that drift tube. In mass spectrometry, we try to pump all of this buffer gas out so we have as low a vacuum as possible and a longer mean-free path. However, in ion mobility, what we want is we want more collisions with buffer gas. So here we try to put as much buffer gas in as we can handle based on our sensitivity and our instrumental conditions, such as voltage, other things. Then we have a weak electric field that pulls the molecules through this buffer gas. And so if we have two ions that have the same M over Z, so in mass spec you would just detect their M over Z, but we have one that's formed in a more of a ring-based structure and the other one is more linear. And if we pulse these in this nice square wave pulse, we can have a race. So our smaller, more ring-based structure is going to get through the drift tube faster than our more elongated structure, and we can get a shape separation where we see that about 40% of our distribution is ring-based and 60% is our linear distribution. So from those drift tube measurements, we can get this ion neutral collision cross-section value. And this value is related to the size and the shape of your ion. And your molecules actually tumble as they go through the drift tube because it is such a weak electric field, it allows them to tumble as they travel. We also can this makes it so this ion neutral part is very important. So part of it is our ion. The second part is our neutral. So that's our buffer gas. And so if we change our buffer gas, our collision cross section is going to change. And you can see here if we put basically this circle around the molecule because it is tumbling. And so it's this rotationally average collision cross section value. Then this circle is going to get bigger if we use something like going from helium buffer gas to nitrogen buffer gas, and it's going to get even larger if we go to something like argon. And so your collision cross-section it's very important to know what buffer gas people are comparing in their measurements. This is also a very robust property, and it's really nice. So if we do comparisons between it and liquid chromatography, where your stationary phase in liquid chromatography usually changes through time based on the molecules that go through that stationary phase, and your retention times might not be as reproducible. Here, our stationary phase is our buffer gas. And as long as we put nice pure buffer gas into our system, then we should be able to get very, very reproducible drift times as whenever we're using our instrument. So because we can take those drift times, move them to the collision cross section, we can also compare these values in different labs because the collision cross section brings into calculation the pressure, the length of the cell, and the temperature. However, again, remember that the drift gas you use in your systems is very important for this value. So to show you how we would do a collision cross-section determination to get the absolute collision cross-section of the molecule in our system, what we do is we put a specific voltage on our system. And so if we have a 10 centimeter cell, say, then this would give us 50 volts per that 10 centimeters, and we would have 5 volts per centimeter would be our electric field. This would give us a arrival time of our molecule at 19 milliseconds. Now, if we up this drift voltage and basically up our electric field, then we can see our molecules are going to travel through the drift tube a lot faster. And we can keep upping that and upping that and upping that, and maybe even one more time. So we usually do this about 5 to 7 times to see how our molecule is depending on that electric field, and you can see that there's going to be some type of linear relationship between those. So then we'll go plot those in this y equals ax plus b relationship, where our pressure and our electric field are on the bottom and our arrival time is on the y-axis. So we can see our nice linear relationship. And we also know that our arrival time is inversely proportional to our reduced mobility. It's proportional to our length squared. And then we have our standard pressure and temperature, and then multiply by pressure over voltage. And then plus our B value is this T naught. So here, because we know our slope is inversely proportional to our reduced mobility, and our y-intercept is this T naught, which is the time outside of the drift tube. And so it's the time it takes for the molecule after it goes through the drift tube to hit the detector. So if you have quadrupoles or collision cells or other things, that's all going to be included in your T naught value. We can then take the reduced mobility and put it in the Mason-Schwamp equation, and it's inversely proportional to our collision cross-section, where we can put in number density, elemental charge, temperature, Boltzmann's coefficient, and reduced mass. So that's a pretty easy relationship to get back to our collision cross-section values. And these drift tube measurements have had great utility in doing a lot of comparisons where we can see how the cross-section of our gas phase molecule compares to something like the crystal form or the NMR structure. So you can look at the difference between gas phase, solution phase, and solid phase. They're also used a lot in looking at other ion mobility techniques. And so because the drift tube only uses a DC-based voltage through that electric field, we can start looking at other techniques that might apply RF potentials, because RF is known to heat things. Then we can see if there's any unfolding occurring in our molecules by looking at the different sizes of the collision cross sections. So when we think about drift tube ion mobility and traveling wave ion mobility, I like to think of things visually. So here I've got a nice water analogy where in our drift tube, we have this nice stream that's flowing towards us. And then for our traveling wave, we have this nice little wave that's moving through our environment. And it's a nice uniform wave. We're also going to have some help from our friends, the turtle twins, Simon and Garfunkel, where they are both the same mass, but Simon wants to go down in a more compact cross section or size than Garfunkel. So if we send Simon and Garfunkel down this water, where the water is very uniform and it's kind of mimicking our electric field, and our buffer gas is basically the atmospheric gas, we can see that Simon makes it to the finish line before Garfunkel does. In our traveling wave, we can see something very similar where Simon's being pushed more by each wave than Garfunkel, because Garfunkel is so big that sometimes he goes over the top of the waves where Simon just keeps getting pushed. And so we can again see that Simon's going to make it to the finish line before Garfunkel is. So in traveling wave, if we get a little bit more into the specifics, you need calibration. So because that wave height can't be adjusted up and down like the electric field and drift tube ion mobility, then we have to have something that we know what the collision cross section is when it goes through that traveling wave. The reason you can't adjust that wave up and down is because you're going to cause either more or less surfing for different molecules sizes if you try to put a higher voltage on your wave or a lower voltage on your wave. And so for a nice little animation, Waters has this great one where we can see some molecules are pushed, like the green one, as it goes through, where other ones are bigger and they're going over each of the waves as it travels through the system. And that allows the molecules to separate into different regions of the waves. So because we need this calibration, though, we can see that we should use similar analyte ions, because sometimes if you're trying to calibrate based on a peptide, but you're running glycan experiments, the peptide might not be the best molecule for the calibration. We also want things that are of similar charge. So here we can see single charge and double charge have different lines for their calibrations. And you can see that you're going to plot the drift time versus the collision cross section to get the new cross sections for the molecules you're measuring. So traveling wave is used very similar to drift tube measurements. And so here we can see that we can look at an unbound protein and then put a drug onto the protein and see how much it changes the size of our molecule. We can do that with drift tube also. Traveling wave can go and do a lot of the things that drift tube can do. The main thing it can't do is it can't do that absolute collision cross-section measurement. We can also use traveling wave for imaging experiments, and this was one of the first the traveling wave instrument was one of the first IMS instruments used in imaging. Here I got the data from Kevin Giles, but I think the first application of imaging was actually John McLean's lab in combination with Richard Caprioli. And this data that Dr. Kevin Giles gave me showed me that if the M over Z's are very close, it can be really hard to separate these guys because they're 0.0003 M over Z or Dalton apart. But using their drift time, if we add that in, we can see that this first molecule is clear over here in the corner of the rat whole body, where the second one is more in the center. And if we plot them together, you can see the different distributions between the two molecules. Now let's go a little bit into field asymmetric ion mobility. So field asymmetric ion mobility is also known as differential mobility spectrometry or differential ion mobility spectrometry. And so you can call it DMS, DIMS, or FAMES. And just remember, all of them end in S. So if you get confused with differential mobility analyzers that ends in A, it doesn't link back to this same technique. So in FAMES, we're using both, we're using the ions mobility, but doing the difference based on the low and high electric field. So here we know that we have an oscillating electric field that's changing, and we can put that either in plates or cylindrical electrodes. So here's our nice plates, here's our cylindrical electrodes. I'm going to illustrate this with our planar FAMs or plated FAMs, just because it's a little bit easier to see. So here in our planar FAMs, we have a uniform gas flow. So this is the first time we've talked about an ion mobility system with a gas flow. And the other two, drift tube and traveling wave, don't have gas flows. So now, if our gas is pushing our molecules this way, then what we do is we put a displacement voltage or a dispersion voltage on this top electrode, where it's alternating between this low to this high field. And because it's asymmetric, we know it's field asymmetric, we're not going to have the same amount of time for the high and the low. You can see here, low in this case is a lot longer time period than our high voltage being applied. So if we have our one little blue ion down here, and we give him this high voltage, he gets pushed away from this electrode and goes down. Now, if he gets a low voltage applied though, now he's going to be more attracted towards that electrode, or not as pushed as far down. So he's going to go up a little bit for that time period, and then down, and then up, and then down. And unfortunately, it looks like this guy is probably going to collide with the electrode before he hits the nice slit where he can escape. Now, so that we can scan these molecules out, because we're not going to change our dispersion voltage, now we want to put a compensation voltage onto our electrode, so that we can pick which molecules come out. So what that allows us to do is, if we have 3 molecules here, by scanning through this compensation voltage, we can select all 3 based on different values for compensation voltage. And that's why you'll hear in FAMs, my compensation voltage I needed to get my molecule out is a specific number. If you don't use the right compensation voltage though, the guys hit the electrodes, and we only get the one out. So FAMs operates at atmospheric pressure. So the other 2 techniques I talked about, a majority of the commercial instruments are at lower pressures, but there are several drift tube systems that are at atmospheric pressure. So it can come in atmospheric pressure too. FAMs has this narrow band filter, so you must scan over CVs to acquire all ions. You have to get them out that little slit. And the measured mobilities cannot be directly correlated to the ion structure, because they're moving different ways in high and low fields. And it's thought that at really high electric fields, the ions could dipole align or do other specific activities that you're not going to see in low field limits. So one great utility of FAMs, there's many, but one great utility is to get ions, is to reduce contaminants and really focus on ions that you're interested in. And so in this case, the researcher, who was Dr. Sue Abatiello, she was interested in looking at proteins. And so she was seeing that there were a lot of +1 ions in her initial spectra. And she was hoping there wasn't any ionization suppression due to these +1 ions. And so what she did though is she turned her FAMs on, and she was able to get rid of those +1s and then focus on higher charge states of her proteins. So we can see her proteins are mainly in +6 to +11 charge states. And she was able to go to a CV area that was excluding the +1 ions and making those hit the electrodes, and only letting the higher charge states get through that slit. So now if we go to differential mobility analyzers, or DMA, these ones are very similar to drift tube in a way, in that you have this uniform electric field. So our electric field is similar to drift tube, but now we have a perpendicular gas flow to our inlet slit, and we have a very tiny exit hole. So while our electric field is pushing our molecules down, our gas flow is pushing them sideways, and then we have to change a few conditions to get the molecules that we're interested to come through that little slit. And so DMA is great for really large molecules though. So it's been used in nano materials, and then also viruses, amyloids, glycoproteins, lipoproteins, all kinds of systems like that. So here's a really nice antibody size distribution. But for DMA, you can directly relate this to the structure. So you can get an absolute collision cross-section out of DMA, both it and DTIMS. You must scan over mobilities though to acquire all ions. So it's similar to FAMES in that is it's a scanning technique. And then our final one that I'm going to talk about is trapped ion mobility spectrometry. So trapped ion mobility spectrometry happens in a funnel. And so you can see this funnel-like device, that's our trapped ion mobility spectrometer. And so here the ions will accumulate in the analyzers, and then they'll start to separate based on their mobilities in that analyzer section. Your calibration is also required, but there's been some recent papers that are showing there's some equations that can directly calculate the collision cross-section. So I'm looking forward to seeing more of those in the future. So here, Bruker loves to do everything orthogonal. So it's designed as an orthogonal entrance, and your molecules will go into this entrance funnel and then start separating in the analyzer. And I have a more detailed schematic next, or I guess animation. So here I'm going to stop him first. So this also has a gas flow in the system. And so the gas flow is going to push your molecules to this analyzer region where there's an electric field that's pushing them back. It doesn't want to let those out. And so this is that analyzer section. Here, then your molecules separate by mobility and you start ramping them out of the instrument. And what happens is actually the biggest ones come out first based on the way that they do the separation. So this allows you to get really good or high resolving power if you slowly ramp the molecules out. And the slower you ramp them, the higher resolving power you get. So in this case, they were doing some phospholipid structures where they had the double bond position, either at position 9 or position 6. Both are in a cis orientation, but they were able to ramp them so slow that they could get a nice resolving power of 203. And I've heard that a majority of the time this takes close to a second. If they need to connect this though to faster techniques like LC or something, they have to go down on their resolving power because they need to have higher throughput for their system. So then their system is operating more at like the 60 to 80 resolving power if you're doing LC timescales. So now let's use our water analogy, and this is where I'll finish up today, and that's about how far I got last time, is to relate all of these ion mobility techniques. And so if we start with our drift tube ion mobility and our traveling wave, we can see that Simon is going to hit the finish line first in both of these cases because he's a more compact structure than Garfunkel. Now, if we add DMA though, we know that DMA has a gas flow. So I'm going to put that as basically a little wind here that's going to go perpendicular to how that electric field, which is the water in this case, is going. And it also has a slit exit. And so those are our little rocks here. So anything that isn't in these specific parameters is going to hit the rocks, and we're not going to be able to see it in our detector. So unfortunately here, Simon got blown off path because he was too small, and we're hoping that Garfunkel can make it through to the detector. So now if we think about trapped ion mobility, this is where we have the gas flow pushing the turtles down or our molecules down, but then we have the electric field is basically pushing them up. So in this case, I have them being stopped by the dam, but the electric field is basically pushing those molecules up, and until we start ramping it, we don't get the molecules out. And so here we have Garfunkel is actually getting pushed more by the gas flow and Simon less, and then we're going to ramp open this dam bridge, or I guess gate, the gate to the dam, and Garfunkel will probably get out first. And then if we go to FAMES, we have that combination of the high field and the low field, and also the gas flow. And so the gas flow here is going to push our turtles down in this high field. The high field is going to be a waterfall condition because we don't know how our turtles are going to respond in that high flow field. Are they going to tumble down the waterfall? Are they actually going to surf down it? And then again, we have a slit. So we have our little rocks down here. So if we don't have the perfect conditions, our turtles will hit the rocks and won't make it to the detector. So we have Garfunkel in the lead again, and he's headed down his high field and getting to the end. But I hope this helps you guys understand the differences between the different types of ion mobility spectrometry. And I hope you can join us on September 16th for my second part of my tutorial. Have a wonderful day, and I'll see you all soon. Bye.